Okay, good morning, my students. So, our materials today is about momentum analysis of flow system. The objective of this chapter, the first, identify the various kinds of forces and moments acting on a control volume, and then use control volume to analyze the forces associated with fluid flow, and then use control volume analysis to determine the moments caused by the fluid flow and the torque transmitted. The first, we must remember the Newton's law. Newton's law is the relations between motion of bodies and the force acting on them. If we talk about the Newton first law, a body at rest remains at rest, and a body in motion remains in motion at the same velocity in a straight path when the net force acting on it is zero. Therefore, a body tends to preserve its state of inertia. Newton's second law mentioned about the acceleration of a body is proportional to the net force acting on it, and it is inversely proportional to its mass. And then Newton's third law. When a body exerts a force on a second body, the second body exerts an equal and opposite force on the first. Therefore, the direction of the exposed reaction force depends on the body taken as the system. So simply, Newton's second law is defined as F equal to ma. F is the force, A is the acceleration, and the push are expressed in vector. And then A is the derivation of velocity with respect to time. And then if the mass changes by the time, the Newton's second law can be expressed as the differentiation of m multiplied with v over dt. M multiplied with v is the momentum. So linear momentum, or just we said the momentum of the body, is the product of the mass and the velocity of the body. Newton's second law is usually referred to as the linear momentum equation. There is a conservation of momentum principle. The momentum of a system remains constant when only the net force acting on it is zero. So in mathematical expression, we mentioned about F, that is the net force, equal to the mass multiplied with acceleration, and then equal to the mass multiplied with the differentiation of velocity with respect to time, and also equal to the differentiation of momentum over dt. So the force is the rate of change of momentum. So Newton's second law is also expressed as the rate of change of the momentum of a body is equal to the net force acting on it. So the parameter mass multiplied with velocity is the linear momentum. So the counterpart of Newton's second law for rotating rigid body is expressed as m equal to I multiplied with A. M is the moment of momentum, and then alpha is the angular acceleration. Either moment of momentum and angular acceleration is expressed as vectors. I, in this expression, is the moment of inertia of the body about the axis of rotation. It can be also expressed in terms of the rate of change of angular momentum, dh over dt. So the angular momentum equation can be expressed as m equal to I multiplied with alpha equals to I multiplied d omega over dt, and then equal to the rate of change I omega over dt, and then the multiplication of I, moment of inertia, and omega, angular velocity vectors, is angular momentum. So it means the moment of momentum is the rate of angular momentum over dt. And then the angular momentum about one axis, for example, x-axis, we can simply express mx equal to ix d omega x over dt. That is equal to d and then hx over dt. Hx is the angular momentum about the x-axis. So the conservation of angular momentum principle mentioned above, the total angular momentum of a rotating body remains constant when the net torque acting on it is zero. And thus, the angular momentum of such system is conserved. So in this equation, we can see that the rate of change of angular momentum, I omega, of a body is equal to the net torque acting on it. So m equal to I alpha equal to the rate of change of angular momentum with respect to time. Okay, the second part of this chapter is choosing a control volume. A control volume can be selected as an arbitrary region in space through which fluid flows, and its bounding control surface can be fixed, moving, or even deforming during flow. So many flow systems involve stationary hardware firmly fixed to a stationary surface, and such systems are best analyzed using the fixed control volumes. For example, we can see in this figure. So for the system, we select the fixed control volume. When analyzing the flow system that are moving or deforming, it is usually more convenient to allow the control volume to move or to deform. So for example, when we analyze the aircraft flying in the air, so we make the moving control volume that is following the whole body of the aircraft. So this is the description of moving control volume. When analyzing flow systems that are moving or deforming. Okay, in deforming control volume, part of the control surface moves relative to other parts. So here, when we see the piston, the cylinder, the cylinder piston. So we make the control volume, for example, in this shape. And then while the piston moving, so the control volume will change, will deform. So for this system, we select the deforming control volume. Okay, so from this page, we can select the fixed control volume, the moving control volume, and the deforming control volume. Okay, the third part of this chapter is the forces acting on control volume. So the forces acting on control volume consist of several forces, and we classified into two forces. The first forces is body forces. The second forces is the surface forces. The body forces acts throughout the entire body of the control volume, such as gravity, electric, and magnetic forces, while the surface forces act on the control surface, such as pressure and viscous forces, and reaction forces at points of contact. Only external forces are considered in the analysis. So the total force acting on the control volume can be expressed as sigma F. That is equal to sigma, the body force, plus the sigma of the surface force. So in this figure, we can see the description of control volume, and then the control volume has the surface, the boundary surface that is called the control surface. In certain position of control surface, we can define the vector perpendicular to that surface. So we call it the normal vectors N, while the force working at the control surface can be in arbitrary direction, and we note it with df surface. So the total force acting on a control volume is composed of body forces and surface forces. The body forces is shown on a differential volume element, dV, and surface forces is shown in a differential surface element, dA. The most common body force is the gravity, which acts on a downward force on even differential element of the control volume. So the gravitational force acting on a fluid element is expressed as dF gravity equal to rho g dV. dV is the elemental volume. G, of course, is the gravity acceleration. And then F gravity is the gravity force working at that volume. Gravitational vector in Cartesian coordinate. Again, we use the unit vectors I, J, K. So the gravitational vector equal to minus G and then K. K is the unit vectors in z direction. And then G. G in this expression is a scalar variable, scalar parameters. And then the total body force acting on control volume can be expressed as the integration for the whole control volume of rho g dV. And then we must remember G is constant, relatively constant. And then rho integral rho dV will become the whole mass of the control volume. So it means the total body force become the mass of the control volume multiplied with the gravity acceleration. Then the total force can be expressed as sigma F. This is total force. And it is equal to the gravity, total gravity force. This is becoming the body force. And then plus the surface forces. The surface forces consist of the total pressure force. So pressure on the surface plus the total viscous force. And then plus other other forces working on the surface. So surface forces are not as simple to analyze since they consist of both normal and tangential components. So the normal stresses are composed of pressure, which always acts inward normal, and viscous stresses. And then the shear stresses are composed entirely of viscous stresses. So if we see this elemental volume, using the Cartesian coordinate, we define x, y, z. And then the gravity acceleration is directed to negative z-axis. This is. And then the elemental gravity force equal to rho dV, so it means the mass density multiplied with the volume of this element multiplied with the gravity acceleration. The gravitational forces acting on a differential volume element of fluid is equal to its weight. The axes have been rotated so that the gravity vector acts downward in the negative z direction. Surface force acting on differential surface element. dF surface equal to sigma ij dot n multiplied with dA. dA is the elemental of area. And then n is the vector normal to the surface, while sigma ij is the stress here, normal stress. And then the total surface force acting on control surface becoming the summation of all surface forces. So we can make the integration for the whole surface. So becoming the integration of control surface and then multiplied with sigma ij dot n multiplied with dA. Then the force, the total force, equal to the summation of the body force plus the summation of surface force, becoming the integration for the whole control volume of rho g dV plus the integration of the whole control surface of vector sigma ij dot n multiplied with dA. And then again remember, the total surface equal to the total body force plus the surface forces here. When coordinates axes are rotated A to B, so for in this figure we have the control surface here, and then at this location we have the perpendicular vector to the surface, so that is normal unit vectors. And then we select the coordinate xy in this direction, x horizontal, y vertical. But in P we use the similar control surface. So it means the normal force at the same location, at the same direction. And then the forces working at the elemental area equal to the case of part A. But in this case, the definition of x and y is rotated. So here rotated at several value counter clockwise here. So when the coordinate axes are rotated from the definition of coordinate at A to the definition of coordinate at B, the components of the surface force change, even though the force itself remains the same. Only two dimensions are shown here. Okay, a common simplification in the application of Newton's law of motion is to subtract the atmospheric pressure and work with gauge pressures. So this is because atmospheric pressure acts in all directions and its effect cancels out in every direction. This means we can also ignore the pressure force at outlet section where the fluid is discharged at the atmosphere, since the discharge pressure in such cases is very near atmospheric pressure at subsonic velocity. So here we can see atmospheric pressure acts in all direction. So if we have the ship here, atmospheric pressure acts in all direction. And thus it can be ignored when performing force balances, since its effect cancels out in every direction. So this is the figure with atmospheric pressure considered. So in this part, we have atmospheric pressure. In this part, we have atmospheric pressure. In this part, we have atmospheric pressure. And this part, we have the pressure plus atmospheric pressure. While in this figure, we can see the pressure working on the body without atmospheric pressure considered. So it means with atmospheric pressure cancelled out. So only in this part, we have the pressure, and this is becoming the resultant pressure. So for this system, we analyze the flow of the fluid in this part. So it means we can define the control volume here we draw with the red dash mark here. So the red discontinuous mark. So the cross section throughout a faucet assembly, illustrating the importance of choosing a control volume wisely. So we can select, for example, following the discontinue line of red color, or we can select the control volume using the discontinuous line with the black color. So with the red color, we said this is the control volume A. With the black color, we said this is the control volume B. So in analyzing the control volume P, the selection of control volume P is much easier to work compared with the control volume A. The control volume A is complicated, but when we define the control volume P, all part of control volume A is occupied by control volume P. The fourth part of this chapter is the linear momentum equation. So the Newton's second law for a system of mass m subjected to the net force sigma f is expressed as sigma f equal to ma equal to m dv over dt equal to d mv over dt. mv here is the linear momentum of the system. So the multiplication between the mass and the velocity vector. Noting that the density and velocity may change from point to point within the system. So the Newton's second law can be expressed more generally as the resultant of the force equal to the rate of change with respect to time of the integration for the whole system, rho v dv. dv here is elemental volume. V here is the velocity vector. So rho v dv is the momentum of a differential element dv, which has the mass dou m equal to rho dv. So the Newton's second law can be stated as the sum of all external forces acting on a system is equal to the time rate of change of linear momentum of system. This statement is valid for a coordinate system that is at rest or move with a constant velocity. We called it inertial coordinate system or inertial reference frame. Okay, so this is the derivation of the relation, and then we use the integration notation. So in elemental expression, we have dmv system over dt that is equal to d over dt integral of control volume rho v dv plus the integral of control surface rho v and then multiplied with vr dot n dA. Vr here is the velocity minus the velocity of control surface. So we use the relative velocity here. So in general, sigma f equal to d over dt, and then integration of control volume rho v dv plus integration for the whole control surface rho v, and then multiplied with v relative vector dot n unit vectors dA. So the sum of all external forces acting on a control volume equal to the time rate of change of the linear momentum of the contents of the control volume plus the net flow rate of linear momentum out of the control surface by mass flow. This is general expression. And then the expression become simpler when we use the fixed control volume. So similar with the expression in general relation, but here the difference is the relative velocity here is replaced with the velocity of the fluid here. So there are another expression. dPc over dt equal to d over dt integration of control volume rho p dv, and then plus integral control surface rho p, and then this is the v r dot n dA. Here P is the multiplication of mv. So this is linear momentum. And then P in here is the velocity vector. So by replacing P with the linear velocity, linear momentum, and then small p with the velocity vector, so we will have this equation that is really equal to the first equation in above. So it means the linear momentum equation is obtained by replacing P in Reynolds transport theorem by the momentum mv and small p by the momentum per unit mass v, large V. Okay, so this equation is known as Reynolds transport theorem, the expression of Reynolds transport theorem. Okay, then suppose we observe the system. The system is 180 degrees elbow supported by the ground. So we can draw the control surface in this shape. So this simple control surface is representing the more detailed control surface if we make in this shape. So this control surface will have the width. Here we can see two-dimensional, yeah. So it means the control surface will have 1 units in the perpendicular direction, so it is becoming the control volume. So it is having the width W. And then of course, since this is the ground, so the ground will give the reaction force FR1. Okay, then here we have the surface. And this surface is noted with the notation A2. And then at this surface, the pressure, the gauge pressure is P2. In other side, the surface, the right hand side surface is A1, and then the gauge pressure is P1. P1 here. Okay. In most flow system, the sum of the forces, sigma F, consists of weight. So this is the weight. And then pressure force. So the force working here and the force working here. And reaction forces. The reaction force given by the ground. So the gauge pressure are used here since atmospheric pressure cancel out on all other side of the control surface. So if we use the absolute pressure, actually, there are pressure here, and then there are atmospheric pressure in this part. There are pressure here, another part here, and then this surface, and this surface until this part, working atmospheric pressure. So the momentum equation is commonly used to calculate the forces, usually on support system or connectors induced by the flow. So this is the previous expression. Of course, here using the fixed control volume. So here we are not using the relative V, but using the V itself. Okay, then there are special cases. If the flow is steady, so the previous equation here, the first time becoming 0. So it means we have the resultant of the force equal only the integration of whole control surface of rho v and then multiplied with the dot product VR and dA. And then if the mass flow rate across an inlet or outlet is noted by m dot. So it means m dot equal the integration of rho and then Vn dAc. So this is equal to rho V average and then multiplied with the AC. And then this expression, so the mass flow rate multiplied with the average velocity of the fluid. This is becoming the momentum flow rate across a uniform inlet or outlet. In typical engineering problem, the control volume may contain many inlets and outlets. At each inlet or outlet, we define the mass flow rate and the average flow velocity. If we see this figure, so we define this is the control volume. And then we have two inlet. So inlet 1 and then inlet 2. And then we have 3 outlet. So the outlet 3, outlet 4, and then outlet 5. So in every inlet and every outlet, we will have a certain mass flow rate and then also the average velocity of the fluid. So examples of inlets or outlets in which the uniform flow approximation is reasonable. In the first figure, the well-rounded entrance to a pipe. And then at the second figure, the entrance to a wind tunnel test section. And then at the third figure, a slice through a free water jet in air. So here, although actually the velocity is in variation at near the wall, but we can assume the whole velocity here equal to the average velocity. So either in well-rounded entrance to a pipe or entrance to a wind tunnel section or a slice through a free water jet in air. Okay, then there is a momentum flux correction factor, beta. The velocity across most inlets and outlets is not uniform. The control surface integral equation may be converted into the algebraic form using a dimensionless correction factor beta, called by momentum flux correction factor. So remember again, in the previous we have the momentum equation in this expression. Then we add the correction factor beta. So this part, this is relating the velocity. And then since the velocity is not really uniform, so we replace with the summation of the fluids going out from the control volume of beta multiplied with mass flow rate multiplied with the average velocity, and then minus the total of the mass flow rate multiplied with the average velocity entering to the system, but multiplied with beta. So the momentum flux across an inlet or outlet becoming the integration of AC, rho v, and then multiplied v dot n dAc. This is becoming the beta m dot multiplied with the V average. Beta is always greater than or equal to 1. So beta is close to 1 for turbulent flow and not very close to 1 for fully developed laminar flow. So from this expression, beta can be defined as the ratio of integral rho v multiplied with dot product of v vector and n vector DAC over the m dot v average. And then the momentum flux correction factor beta. Beta from this expression can be simplified into this expression 1 over AC integral AC and then the square of V over V average multiplied with the AC. Okay, in this example, consider laminar flow through a very long straight section of round pipe. So it is shown that the velocity profile through a cross-sectional area of pipe is parabolic here, parabolic, with the axial velocity component depending on the radial position from the center. So the velocity, the profile of V equal to 2 times the V average and then multiplied with 1 minus r square over large R square. So large R square is the radius of the inner pipe, while small r is the position observed from the center of the pipe. Then calculate the momentum flux correction factor through a cross-section of a pipe for the case in which the pipe flow represents an outlet of the control volume as sketched in this figure. Okay, so for this case, we make the assumption. The first assumption, the flow is incompressible and steady. And then the second assumption, the control volume slices through the pipe normal to the pipe axis as sketched in this figure. Okay, for the analysis, we substitute the given velocity profile V in this equation. And then integrate, noting that DAC, of course, is circle, becoming 2 PR dr. So we have the elemental area for certain position from the center of the pipe. Okay, if okay, previous page, beta equal to 1 over AC, and then integral AC, and then the square of V over V average DAC. And then we apply that. We select the elemental of area is in circle. Okay, so it means we will have 4 over pi r square and then integral 0 until r. And then we follow the velocity profile here. 1 minus r square over large R square. And then TAC itself are of course becoming 2PR TR. So actually we see the circle, and then the circle has the width dr. Okay, 4 over PR square. This is coming from this expression. So phi over phi average. And then phi over phi average, we have 2. 2 and then square becoming 4 here. And then AC itself, of course, is the area of the inner pipe, PR square. Defining a new integration variable, y equal to 1 minus r square over large R square. Then we can make dy, of course, becoming minus 2r coming from minus r square. And then over r square dr. So we make the differentiation of y with respect small r. Also, y equal to 1 at r equal to 0. Because if we replace r equal to 0, so y equal to 1. And y equal to 0 if small r equal to large R. So this part becoming 1 square. 1 minus 1 square will become 0 here. And performing the integration of the momentum flux correction factor for fully developed laminar flow becomes in this expression. So beta equal to minus 4 integral 0 until 1 y square dy. So we have replaced this equation by the new definition in y here. So the integration of this expression becoming minus 4. And then, of course, this is becoming y power 3 divided by 3. And then the boundary of the integral is from 1 until 0. So the result becoming 4 over 3. So that is the example of calculation of momentum flux correction factor for laminar pipe flow in this figure. So for turbulent flow, beta may have an insignificant effect at inlet and outlets. But for laminar flow, beta may be important and should not be neglected. It is wise to include beta in all momentum control volume problem. Okay, again, in steady flow, steady linear momentum equation can be written as sigma F equal to sigma beta m dot V for the outlet minus sigma beta m dot V for the whole inlet. The net force acting on the control volume during steady flow is equal to the difference between the rates of outgoing and incoming momentum flows. So you can see in this figure where the system has 2 inlet and 3 outlet. So the net force acting on the control volume during steady flow is equal to the difference between the outgoing and incoming momentum fluxes. So the expression of beta m dot V for out, of course, is the summation between beta 3 m3 dot V3 plus beta 4 m4 dot V4 and then plus beta 5 m5 dot V5 dot, while the total summation of beta m dot V, of course, equal to beta 1 m1 dot V1 plus beta 2 m2 dot V2. Now we see the steady flow with one inlet and one outlet. So the expression, the resultant of the force resulted in the system becomes simpler. So this is becoming m dot and then multiplied with beta 2 V2 that is happening in outlet. And then minus beta 1 V1 that is happening in inlet. And then if we observe the system where the flow is only along x coordinate, so we can write simply only in x coordinate. So that is the resultant of the force in x direction equal to m dot and then beta 2 and then velocity 2 in x direction minus beta 1 and then velocity inlet along x direction. So this is the example of control volume with only one inlet and outlet. Okay, then here we have the system. The system having the fluid flow. The direction of the fluid flow is in this direction. So we can define the fixed control surface. For example, using this shape. So what is important here in this part? We define the control surface where the area is perpendicular to the velocity. And then here also, we define the control surface where the area is perpendicular to the fluid entering to the control surface. While for the reaction given by the ground, in general, we can place FR in this direction. So it has component in X direction, it has component in Y direction, positive. Okay, if we draw. If we draw the parameter of beta multiplied with the mass flow rate multiplied with the velocity. So this part, beta 2 m dot and then v2 in this direction. So we can draw in this direction. And then beta 1 m dot v1 in this direction. But to express this relation, the sign is negative. So it means the vector beta 1 m v1, which is in this direction, should be reversed. So the direction will be in the reverse direction, minus beta 1 m v1. And then we just use the rule for vector summation. If we must add this vector with this vector, so it means the result will be a vector starting from the starting point here and then ending with the ending point of this vector. So it means this vector plus this vector, we will have the resultant force, this vector. So the determination of the determination by vector addition of the reaction force on the support caused by a change of direction of water. So FR in this direction. So we can make parallel lines, and then the magnitude similar magnitude. So that is the real reaction force vector given by the ground. Okay, if we see the flow with no external force. So it means the resultant of the force equal to 0. And then the other times similar expression such as in the previous page. So we have 0 equal to dmv cv over dt, and then plus there is the total summation of beta m dot v at the outlet minus the summation of total beta m dot v at the inlet. So in the absence of external force, the rate of change of the momentum of a control volume is equal to the difference between the rates of incoming and outgoing momentum flow rates. So we can reorganize this equation, and then we will have this expression. So it means here F thrust will equal to M control volume and then multiplied with the acceleration. That is equal to this value. So imagine we move this time to other side. So it means this part becoming negative and this part becoming positive. So that is we have the positive and then summation of inlet minus the summation of beta m dot v outlet. So the application of this relation, for example, in the rocket. So the thrust needed to lift the space shuttle is generated by the rocket engines as a result of momentum change of the fuel as it is accelerated from about 0 to an exit speed of about 2000 meters per second after combustion.